Hello everyone. Good morning students. Today we are going to discuss about the action potential of the nerve. Nerve signals are transmitted by action potential, which are rapid changes in the membrane potential that spread rapidly along the nerve fiber membrane. Each action potential begins with a sudden changes from the normal resting negative membrane potential to a positive potential and ends with an almost equally and rapid changes back to the negative potential. The duration of the nerve action potential is and is zero point 0.3 meter second. To conduct a nerve signal, the action potential moves along the nerve fiber until it comes to the fiber's end. The changes that occur at the membrane during the action potential with the transfer of positive charge to the interior of the fiber at its onset and the return of positive charges to the exterior of its end. Graphically, and the successive changes in the membrane potential over a few ten thousandths of a second, illustrating the explosive onset of the action potential and the almost equally rapid recovery. The successive stages of the action potential are as follows. Resting stage. The resting is the resting membrane potential before the action potential begins. The membrane is said to be polarized during this stage because of the minus 90 millivolt negative membrane potential that is present. Minus 90 millivolt negative membrane potential that is present, and this is the resting membrane potential. Now we comes to the depolarization state. At this time, the membrane suddenly becomes permeable to the sodium ions, allowing tremendous number of positively charged sodium ions to diffuse to the interior of the axon. The normal polarized state of minus 90 millivolt is immediately neutralized by the inflowing positively charged sodium ions, with the potential rising rapidly in the positive direction. A process called depolarization in large number fibers in large nerve fibers, the great excess of the positive sodium ions moving to the inside cause the membrane potential to actually overshoot beyond the zero level and to become somewhat positive. In somewhat smaller fibers as well as in many central nervous system neurons, the potential merely approaches the zero level and does not overshoot to the positive state. The repolarization state within a few ten thousandths of a second after the membrane becomes highly permeable to the sodium ions, the sodium channel begins to close and the potassium channels opens to a greater degree than normal. Then rapid diffusion of the potassium ions to the exterior re-establishes the normal negative resting membrane potential, which is called repolarization of the membrane. To explain more fully the factors that cause both depolarization and repolarization, we will describe the special characteristics of the two other type of transport channels through the nerve membranes, the voltage gated sodium and potassium channels. And the last, the rectification. The return of the membrane to its original ionic state is achieved through continued action of its sodium potassium electrogenic pump. Voltage gated sodium and potassium channels. The necessary factor in causing both the depolarization and repolarization of the nerve membrane during the action potential, the voltage gated sodium channel, a voltage gated potassium channel also play an important role in increasing the rapidity of the repolarization of the membrane. These two voltage gated channels are in addition to the sodium potassium pump and the potassium leak channels. First, we see the activation and inactivation of the voltage gated sodium channel. For this, we have to view the next slide, in which diagram has been explained all the things. The upper panel, this upper panel shows the voltage gated sodium channel in three separate states, 1, 2 and 3. These three different stages of the voltage gated sodium channel. This channel has two gates, one near the outside of the channel called the activated gate. This is activated gate, and another near the inside called the inactivation gate. This is the inactivation gate. The upper left of the figure depicts the state of these two gates in the normal resting membrane when membrane potential is minus 90 millivolt. This is the state of the activation and inactivation gate during the resting membrane potential of minus 90 millivolt, which activation gate is closed. In this stage, the activation gate is closed, which prevents any entry of the sodium ions to the interior of the fiber through these sodium channels. And we can say that no sodium can enter through the activation gate during the resting membrane potential. Now, the activation of the sodium channel takes place when the membrane potential becomes less negative. Then during the resting state, rising from minus 90 millivolt to 0, it finally reaches a voltage equally somewhere between minus 70 and minus 50 millivolt that cause a sudden conformational change in the activation gate, flipping it all the way to the open position. During this activation state, sodium ion can pour inward through the channel, increasing the sodium permeability of the membrane as much as 500 to 5000 fold. In second diagram, it explains that as the sodium enters into the nerve fiber and membrane potential becomes minus 70 and minus 50 millivolt, it opens the activation gate of the sodium channel. So, opening of the activation gate of the sodium channel increases the permeability of the membrane to the 500 to 5000 fold. Now, inactivation of the sodium channel. This upper right part, this part, so explain this thing. The third state of the sodium channel, the same increase in the voltage that opens the activation gate also close the inactivation gate. The inactivation gate, however, close a few 10 thousandths of a second after the activation gate opens. And that is the conformational change that flips the inactivation gate to the closed state. Is a slower process than the conformational change that opens the activation gate. Therefore, after the sodium channels has remained open for a few 10 thousandths of a second, the inactivation gate closes and sodium ions no longer can pour to the inside of the membrane. At this point, the membrane potential begins to return towards the resting membrane state, which is the repolarization process. It means it says that once the activation gate is opened for the sodium ions, this activation gate and inactivation both gate, though opening of the both gate, this state remains only for few 10 thousandths of a second, few 10 thousandths of a second times is the time for that activation and inactivation gate is remains opened. After that, this inactivation gate is closed, so that again the permeability for the sodium ion is reduced and no longer sodium and ion can pour into the nerve fiber. That this is the events again repolarization state, beginning of the repolarization process. Another important characteristics of the sodium channel inactivation process is that inactivation gate will open, will not reopen until the membrane potential returns to the near of the original resting membrane potential. Therefore, it is usually not possible for the sodium channel to open again without first repolarization of the nerve fiber. It says that once the inactivation gate is closed, it is not reopened until the resting membrane potential is achieved. Now we comes to the voltage gated potassium channel and its activation. These lower two diagrams explains the potassium channel and its activation. Voltage gated potassium channel in two states. During the resting stage, left, and towards the end of the action potential is the right. Towards the end of the action potential, this is the resting state where nerve fiber or membrane having the resting membrane potential of minus 90 millivolt. And the second diagram explain the action potential of the membrane. During the resting state, the gate of potassium channel is closed. Resting state, the potassium channel is closed, and potassium ions are prevented from passing through this channel to the exterior. When the membrane potential rises from minus 90 millivolt towards the zero, this voltage channel changes cause a conformational change and opening the gate and allow increased potassium diffusion outwards through the channel. However, because the slight delay in the opening of the potassium channel, for most part, they open just at the same time that the sodium channels are beginning to close because of the inactivation. Thus, the decrease in the sodium entry into the cell and simultaneously increase in the potassium exit from the cell combines to speed the repolarization process, leading to full recovery of the resting membrane potential within another few 10,000ths of a second. The voltage clamp method for measuring the effect of voltage on opening and closing of the voltage gated channel. The original research led to quantitative understanding of the sodium and potassium channels was so ingenious that led to a Nobel Prizes for the scientists responsible, Hodgins and Huxley. Voltage clamp method, which is used to measure the flow of the ions through the different channels. Two electrodes are inserted to the nerve fiber. One on those electrode is used to measure the voltage of the membrane potential and another is used to conduct electrical current into the or out of the nerve fiber. The investigator decide which voltage the investigator decide which voltage to establish inside the nerve fiber. Electronic portion of the apparatus is then adjusted to the desired voltage, automatically injecting either the positive or the negative electricity through the current electrode at whatever rate is required to hold the voltage as measured by the voltage electrode at the level set by the operators. When the membrane potential is suddenly increased by this voltage clamp from minus 90 millivolt to the 0, the voltage gated sodium and potassium channels opens and sodium potassium ions begins to pour through the channels. To counterbalance the effect of these ion movements on the desired setting of the intracellular voltage, electrical current is injected automatically through the current electrode of the voltage clamp to maintain the intracellular voltage at the required steady 0 level. To achieve this, the current injected must be equal to but of the opposite polarity of the net current flow through the membrane channels. To measure how much current flow is occurring at each instance, the current electrode is connected to an oscilloscope that records the current flow. Finally, the investigator adjusts the concentration of the ions to the other than normal levels, both inside and outside of the nerve fiber, and repeats it the study. The experiment can be performed easily when using large nerve fiber removed from the some invertebrates, especially the giant squid axons, which in some cases is as large as 1 millimeter in diameter. Another means the studying of the flow of the ions through the individual type of the channel is to block one type of channel at a time. For instance, the sodium channel can be blocked by a toxin called tetrodotoxin when it is applied to the outside of the cell membrane where the sodium activation gate are located, and conversely the tetraethyl ammonium ion block the potassium channel when it is applied to the interior of the nerve fiber. Now we comes to the summary of the events that cause the action potential. In a summarized way, we can say that the sequential events that occur during the and shortly after the action potential, the bottom of this figure shows the changes in membrane conductance for the sodium and potassium ions. This is for the sodium ion and this one for the potassium ion. During the resting state, before the action potential begins, the conductance of the potassium ion is 50 to 100 times as great as the conduction of the sodium ions. The this disparity is caused by much greater leakage of potassium ion than sodium ions through the leak channels. However, at the onset of the action potential, the sodium channel intensely becomes activated and allow up to 5000-fold increase in sodium conductance. The inactivation process then closes the sodium channels within another fraction of millisecond. The onset of action potential also causes voltage gated in the potassium channel, causing them to begin opening more slowly a fraction of the millisecond after the sodium channel opens. At the end of the action potential, returns the membranes to the potential to the negative state, cause the potassium channels to close back to other original state, but again only after an additional milliseconds or more delay. This middle portion of this figure shows the ratio of sodium to potassium conductance at each instance during the action potential. The above this depiction is the action potential itself. During the early portion of the action potential, the ratio of sodium to the potassium condensate increases more than 1,000 folds. Therefore, far more sodium ions flow to the interior of the fiber than do the potassium ion to the exterior. This is what caused the membrane potential to become positive at the onset of action potential. Then the sodium channel begins to close and the potassium channel begins to open, and thus the ratio of the conductance shift fall in favor of high potassium conductance but low sodium conductance, and this allow very rapid loss of the potassium ions to the exterior but virtually zero flow of the sodium ions to the interior. Consequently, the action potential quickly returns to its baseline level. Role of other ions during the action potential. Thus far, we have considered only the role of sodium and potassium ion in generation of the action potential. At least two other types of ions must be considered: negative anions and calcium ions. The impingement of the negatively charged ions inside the nerve axon. Inside the axon are many negatively charged ions that cannot go through the membrane channel. They include the anions of the protein molecules and of many organic phosphates, compound, sulfate compounds, and so forth. Because of these ions cannot leave the interior of the axon, the deficit of the positive ions inside the membrane leaves an excess of these impermanent negative anions. Therefore, these impermanent negative ions are responsible for the negative charges inside the fiber when there is a net deficit of the positively charged potassium ions and other positive ions. The increased permeability of the sodium channels when there is a deficit of calcium ions. The concentration of the calcium ions in the extracellular fluid also has a profound effect on the voltage level at which the sodium channels becomes activated. When there is a deficit of the calcium ions, the sodium channels becomes activated, opened by a small increase of the membrane potential from its normal, very negative level. Therefore, the nerve fiber becomes highly excitable, sometimes discharging repetitively without provocation rather than remaining in the resting state. In fact, The calcium ion concentration needs to fall only 50% below normal before spontaneous discharge occur in some peripheral nerves, often causing muscle tetany. Muscle tetany is sometimes lethal because the tetanic concentration of the respiratory muscles. The probable way in which calcium ions affects the sodium channel is as follows. These ions appears to bind to the exterior surface of the sodium channel protein molecule. The positive charges of these calcium ions in turn alter the electric state of the sodium channel protein, thus altering the voltage level required to open the sodium gate. Initiation of the action potential. Up to this point, we have explained the changing sodium and potassium permeability of the membrane as well as the development of the action potential itself, but we have not explained what initiates the action potential. A positive feedback cycle opens the sodium channel. First, as long as the membrane of the nerve fiber remains undisturbed, no action potential occurs in the normal nerve. However, if any event causes enough initial rise in the membrane potential from minus 90 millivolt towards the zero level, the rising voltage will cause many voltage gated sodium channels to begin opening. And this occurrence allows rapid inflow of sodium ions, which causes a further rise in the membrane potential, thus opening still more voltage gated sodium channels and allowing more streaming of the sodium ions to the interior of the fiber. This process is a positive feedback cycle that once the feedback is strong enough continues until all the voltage gated sodium channels have become activated, opened. Then within another fraction of the millisecond, the rising of the membrane potential causes closure of the sodium channels and opening of the potassium channels, and the action potential soon terminates. Threshold for the initiation of the action potential. An action potential will not occur until the initial rise in the membrane potential is great enough to create the positive feedback described in the preceding paragraph. This occurs when number of the sodium ions entering the nerve fiber becomes greater than the number of the potassium ions leaking from the fiber. A sudden rise in the membrane potential of 15 to 30 millivolt is usually required. A sudden increase in the membrane potential in a large nerve fiber from minus 90 millivolt up to about minus 65 millivolt usually cause the explosive development of action potential. This level is minus 65 millivolt is said to be the threshold for the stimulation. Local potential. Not all the stimuli in an action potential. Small stimuli may result in local changes in the cell membrane potential that are below the threshold for the initiation of the action potential. The small changes in the cell membrane potential are called local responses and can be differentiated from the action potential. The refractory period. The nerve cannot respond to a second stimulus during much of the action potential and even longer. This is referred to as the refractory period of the nerve. In fact, refractory period is further divided into an absolute refractory period and a relative refractory period. The absolute refractory period is the period of the action potential when the nerve cannot respond to a second stimulus, no matter how strong it is. The mechanism for the absolute refractory period is a large number of the sodium channels are inactivated and cannot open until the membrane returns to its resting state. A large number of sodium channels inactivated and channels cannot open until the membrane returns to the resting state is the absolute refractory period. The relative refractory period is the period during the action potential where the nerve cannot respond to the second stimulus provided it is greater than threshold strength. The period during the action potential where the nerve can respond to a second stimulus provided it is greater than the threshold strength. For this, there is a mechanism. In the initial part of the relative refractory period, some sodium channels are still inactivated. Throughout the relative refractory period, potassium conductance is high, which opposes depolarization. This is the mechanism of the relative refractory period. Thank you for watching this video. Have a good day. This is the topic of the action potential of the nerve.